This video will talk about the definition of a partially ordered set, also known as a poset, and I'll also talk about how to create the Poset diagram of some poset. So the first thing is a reminder, we've talked about this before, a partial order. Partial order is a type of relation. It's always going to be on two building sets. The first coordinates of the ordered pairs in the relation as well as the second coordinates of the ordered pairs in the relation are both coming from the same set, A, so it's a subset of A cross A. And remember, partial order has the following three properties. It looks almost like an equivalence relation, except there's a change. It's reflexive and transitive, the same as an equivalence relation, but it's also anti-symmetric. So just to remind ourselves, reflexive in terms of the digraph meant for every single vertex you had a loop at the vertex, or in terms of the ordered pairs, you had all of the ordered pairs that were the doubles, A comma A. In terms of anti-symmetric, if you had two different vertices in the digraph, then there is at most one directed edge or one arrow between the two different vertices. It's totally fine if there's no relation between the two vertices. You just can't have two arrows, one going in both directions. Or in terms of the ordered pairs, if A comma B is inside of your relation, then you know the opposite, or B comma A, is not inside of your relation. And remember, we had both asymmetric and anti-symmetric. The only difference was the anti-symmetric, it was totally fine to have loops in your digraph. And that's important because we got to be reflexive here too. And remember, for transitive, this one was if you had A was related to B and B was related to C, that you knew for sure in your relation, then you would be able to find somewhere else in your relation or in the digraph there was a shortcut for every length 2 path, a single length 1 path of A to C. Or in ordered pairs, if you had A comma B and B comma C in your relation, you were guaranteed to also have A comma C in your relation. Okay. Now we've had all that already. A partially ordered set is that building set A with whatever partial order relation it corresponds with set A. In terms of notation, we typically indicate both who the set is. So the set here is written first, and then after it, we write whoever the relation is, the name of the relation. It is also pretty common to see, if you're looking this up either on the internet or a different textbook, where you have your name of your set first, and some people, just to indicate that you're dealing with a partial order, will use the placeholder symbol of a less than or equal to symbol. That's a stand-in for saying, hey, you've got a partial order. So let us look at a potential example here. So this example has a building set of the integers 1 through 5, and the relation says element A is related to element B exactly when A is less than or equal to B. So let's go ahead and actually write out this relation, and then we'll be able to tell if our original set 1 through 5 is a poset with respect to this particular relation. Well, this tells us that the first element has to be less than or equal to the second element. So in this setting, we get 1 comma 1, 1 comma 2, 1 comma 3, 1 comma 4, and 1 comma 5. Notice that's because every number is going to be equal to the first number 1 or bigger. Now, when you start with 2, what do we have? Well, we have 2 comma 2, and then everybody up until we get to 2 comma 5. Whoops, I wrote the 5 first. And then we're going to do the same thing with each of the next guys, or each of the next elements of A. And notice as we keep increasing through our elements of A, we get fewer ordered pairs each time. And when we get all the way up here to our ordered pairs that start with 5, there's only one element in A that's equal to 5 or bigger, namely 5 itself. So that gives us all of the ordered pairs in this particular relation. Now, in order for A to be a poset, the only thing you have to check is the relation R a partial order? Well, let's check that out. So if we look to see if R is reflexive. Wow, I can't spell reflexive. Reflexive. What do? Well, we can simply look for all of the ordered pairs of 1, comma 1, 2, comma 2, 3, comma 3, 4, 4, and 5, 5. And notice we have all of them. So A, comma A is inside of R for all elements of A, which means we are reflexive. Now the next thing, and again I'm just going to do this by way of visual inspection. If we look at the anti-symmetric property, what happens? Every ordered pair you have, if you reverse it, it needs to not be in the relation. So if we start off with the ordered pair 1, comma 2, flip it, you'll get 2, 1. 2, 1 is not in the relation. And notice I'm ignoring the guys that would correspond to loops. Okay. If we look at 1, 3, we reverse it and we say that 3, 1 needs to not be in the relation. Okay, check. 1, 4, reverse it. 4, 1 shouldn't be in the relation. Check. 1, 5, well, reverse it. 5, 1 shouldn't be in the relation. Okay, we're still good. Skip the double 1. 2, 3. All right, well, 3, 2 isn't in the relation. We're good. Flip this guy. Missed a parenthesis there. So if we reverse the order, we'll get 4, 2. 4, 2 is not in the relation. Reverse the order. 5, 2. 5, 2 is not in the relation. And if you keep checking, that will happen for all of these guys. So anti-symmetric, yep, we're anti-symmetric as well. And then the last one here is the transitive property. Transitive. And this one is what we're looking for is if we have two ordered pairs where the middle parts are the same, are we always guaranteed to have the related ordered pair of 1, comma C? In other words, it's like merging the two ordered pairs together. Well, let's see. I won't go through all of the examples, but I'll go through a couple of examples. Suppose we pick on the ordered pair 1, 2. So if that's the AB, we then need to look for somebody that starts with a 2. So maybe we have somebody like 2, 3. So then 1 would be A, B would correspond to 2, and 3 would correspond to C. So that means we're now looking for the ordered pair 1, 3. Check. We've got it. Okay? And it turns out if you check all of those 3 sets, or really pairs of ordered pairs, we'll always get the third one. So that means this guy is also transitive, but I'm going to skip out and checking all of the pairs. Which means that the conclusion here is our set A with this particular relation is a poset.